GC, Instrumentation, Common Detector, FID. John, what does GC stand for again? Gas chromatography. How about the FID part there, here, Andy? Yeah, something detector. She's exactly right. Anyone remember?
Ion,
Flame ionization. Flame ionization detector. Okay. Sandy, we'll get to that. Teamwork. Sandy, what's the mobile phase in GC? A gas. Yeah. What gas is it, Pablo, upstairs? Have you done the GC yet? No. Okay. Oh, you did the GC, right? Who's done the GC? Okay, Adriana, what type of gas is the mobile phase? Hydrogen, right? Is hydrogen explosive? Alice? Highly. Is it explosive by itself, though? Kathleen, what needs to be present for hydrogen to be explosive? Well, yeah, you need some kind of ignition source. You're right. However, hydrogen shooting out of a nozzle hydrogen actually heats up when it expands, so it can self-ignite. So you don't even need a flame then. But what is necessary? Oxygen. All right. If there's no air around or oxygen, it's not going to explode on you. Okay.
They use argon sometimes? Or?
They used to use helium, but helium is getting so expensive. Yeah, it's just we're running out of it. The planet only has so much.
Birthday party.
And
Yeah, I don't say.
yeah, it's hard to get. Why, thinking about gases, you've been on an airplane and, oxygen cylinders. What's the big danger there? Are they explosive? Oxygen?
Yeah.
It's a misconception.
There has to be some kind of
What is oxygen going to combine with to explode?
No, it's kidding. A fuel source.
Oxygen really helps things burn, but oxygen by itself, it's not going to do squat. It'll just make people, maybe a little happier because there's more oxygen. What is the danger with an oxygen cylinder?
Just a really high pressurized fragment or shoot around.
Yeah, I mean, that's just it. It's very high pressure, and it's a steel cylinder. Nothing's going to happen to the cylinder. The problem's the valve, right? Someone knocks it over or something, and then you got a flying missile in a airplane, which isn't a good idea. Right? Okay. Almost all gas chromatography, McGee, utilizes capillary columns. At the head of the column, when doing GC, the sample is vaporized since it's a gas. Okay. When using capillary columns, analyze partitioned. Emily, what's partitioned? Between the mobile phase and the liquid phase. What's partitioned?
It's cut in half or separate.
Yeah.
Fraction.
Yeah. They want you to be. I think they kind of use a special word, kind of a good idea. It's not just separated. I mean, there's an actual affinity, right? These different compounds have different affinities for the stationary phase. That's like dissolves like story. So there's some partitioning going on. It's not equal division, equal separation. It's partitioning. Depends on the compounds. So that's kind of a better word than separate. Okay. So anyway, you have a liquid phase, right? Inside this capillary column. And somehow they get this liquid in there. And I did a research stint with NASA, and so I think I have an idea how they make these things. But how they get a nice uniform lining of glass in there of the liquid in there I'm not so sure. But they had, there's this area in NASA mostly farms everything out now. The researchers there was kind of a sad thing, really. Because, you grow up learning about NASA and the researchers, man, I would love to go be an astronaut or work for NASA or whatever. I can do more research here than my researcher out there at NASA. He didn't have any money. Pretty much all he had is stuff coming across his desk from different universities, and they're proposing to do this research or that research or this research. And that's pretty much all he does. He reviews these and says, okay, you do this, you do that. And I did it for 2 years. The second year, things got even sadder. Because they had, I don't want to shoot anybody's dreams down, but the point is there was this competition, and that's how NASA does it. A little competition to do Project X. They wanted to send out, it was a Mars mission of some sort, and it was more like just a component of it, the rocket. And everyone submitted their work, and there was this one prize researcher at NASA, at the same facility I was at Langley, and everyone thought, hey, he should get it, right? Because everyone was there, and he didn't get it. So I mean, NASA's own prize researcher, it was chosen someone else. I think it was MIT or somewhere, right? So NASA is. I don't know, but it's anyway. The story, what I was getting at, is to make these. The group I was in was working with fiber optics, and hydrogen is a rocket fuel. The hydrogen sensor that they have now is pretty much just a electric circuit, the filament, because hydrogen around platinum kind of heats up and you can sense it. But if you have an electric circuit, what happens? You can have a short circuit in an electric circuit. A little spark, boom, that's not the kind of sensor you want. So what they're working on is fiber optics, because fiber optics, you can put it anywhere. Harsh environments, or what do you call it, shooting off, rockets shooting off, or out in space. Extreme harsh environments, glass works great. Have the coating on the fiber optic, and you can sense it. And you just need a material that can, sense hydrogen. And that was a research project that we had. It's one of these posters, and that's kind of where things kind of fizzled out. But I was going to submit this work and whatever, but we just never got around to it. There's real problems with it. I don't think it would have gone anywhere, but I have a neat demonstration out of it. I don't know if I ever showed you guys this. I only show it in general chemistry when we're talking about catalysts, where I'm going to fill a tube with hydrogen, right? First, you blow up a hydrogen balloon, show how explosive it is. Okay, and then I have a container of hydrogen, and then I transfer the hydrogen gas into a little Erlenmeyer flask, and it's got this black powder in there, and then once the hydrogen gas gets in there, the black powder turns green. So that's perfect for a little sensor. The problem is how do you regenerate it? So that's kind of a problem, but it's kind of self-regenerated. The real problem is that hydrogen is explosive at very low concentrations. And my sensor, or our sensor that we developed, it really only works at really, really high concentrations. So the explosion would happen way before our sensor even sensed it. but I guess it's a start. Anyway. The whole point of this story was how do you make these capillary columns, and all they have this big hunk of glass hanging high in this tower, and it's heated up, and just a little tiny string pulls out, right? And then once you get it going, right, but it's not just glass, it's coated, because we're going to talk about why, but you get this little tiny string going, and you'll pull out enough until you finally get it to the length you want, and you can make it a capillary, you can make it whatever you'd like. And I think somehow that's how they're getting that liquid in there. That they probably have, I don't know, because it's so dang hot, how the liquid wouldn't boil off. I don't know. It's all patented, right? They're not going to say how they do this. But what is the, we'll get to it. The GC instrumentation flow diagram. What's the Mickey Mouse looking thing there, Sandy? What's this? You'd use the GC, right? You had to read, to give you a hint, you had to read this and put it in the GC logbook. Is the gas, so it's an R. The pressure reader, the regulator is the technical word for it. That's the regulator, right? So it's at the head of the mobile phase. That's our mobile phase, our gas cylinder, or mobile phase, whatever you want to call it, right? In our case, it's hydrogen. And there's two of them. One of them reads the pressure inside the tank, and the other one reads the pressure going out of the cylinder, right? So it goes out of the cylinder, right? And all that stuff, you recognize the green nut? That's the inlet, exactly. There's our inlet, right? Okay, so that's where Rob said it's supposed to vaporize, whatever you inject, right? And then it's going to go round and round and round and round in about 60 meters of what? The column, right? Yeah, this thing, right? And then it ends up going to our detector. Well, 60 meters, 30 meters there. Yeah, it's a gas, so you need a length of it. Let's see, so here's our column. Now, what is the dashed line? What's the purpose of the dashed line? Yeah, it's a box, but better word than box is, here's an O, oven. Because with GC, you change the what to do chromatography? You change temperature. It's an oven. And I'm not very good at drawing a great big fan, but behind that 30 to 60 meters of column is this great big fan that can change the volume of the air really fast in there. So it can really very strongly control the temperature to the 1/10 of a degree and ramp it up or down, whatever you'd like. Okay, I think we have most everything in there. Oh, the computer, what would the computer be hooked up to in this case? The detector for sure. Why would it be hooked up to the inlet? You're right. All right. When you stick that syringe in there, does it automatically know that you stuck the syringe in the green nut? No, you had to push some start button. So that's not why it's hooked up. That's not why there's an electrical connection to the inlet. And you're gonna see why later on. But what's so special about the inlet?
It's FID and
Well, there's two. There's actually two green nuts. You're right. One goes to each different detector, but it's not electrical. Those are just two different setups, two columns in there. Yes. You in the program, the software, you set this idea of split and splitless, and we'll talk about that, right? You can actually dilute your sample. So using the computer. Okay. Here's a photo of it. Okay, Pablo, what do you recognize in here? Okay, he sees a big fan. And I guess that orange thing he's seeing is the column, right? Okay. What else do you recognize? Where's the inlet? Top left. Yeah, do you see it going in here? There's our column. There's our inlet. Yeah. It's hard to tell which is which. Only if you use the GC do you know that the inlet's on the right-hand side. Or, sorry, the left-hand side, right? Inlet's on the left-hand side of this machine when you're facing it. And the whole thing is, the whole thing is inside a oven, yeah. Nice big insulated door when you pop it open and closed. Okay. Flame ionization detector. That's this thing. Right? How does it work? There's a nice picture there. Alice can explain it to us. How does what does it stand for again? Flame ionization detector. Okay. How does it work, Alice? Here's all the little parts if it helps you. All right, I got Got a little electrical connection here going to this top part. All right. I don't know if it really helps to tear it all apart, but there's some funky stuff going on in here. All right. But the only thing that makes sense to me is that there's an actual hole there, and I have an electrical connection at the top. What would the electrical connect? Yeah, well, the hole for the flame, right? So on the GC, you don't want to. There's a little tiny sticker that says "Don't put paper up here." I don't know if you've noticed it, but yeah, you probably shouldn't. And if you look in there, I don't even think you can see the flame. Maybe if you shut the lights off in the room. But what's the little electrical connection for? It's got to be measuring something. What is it measuring? FID is a what counter? Carbon counter. Yeah, you can pass that around. Carbon counter. Yeah, he remembers that. This is about as far as we got in analytical. I don't know if we even got this detailed, but carbon counter. Because it's just something that nature does. If you can burn something at a high enough temperature, well, you burn something, what are you supposed to get? You take some wood and you burn it. You're supposed to get what and what? Carbon dioxide and water, right? Yeah, essentially liquid water is so hot it probably vaporizes. But okay, but if you heat it, if you burn something at the temperature of a hydrogen flame, I should Google what that temperature is, but it's really hot. Okay, you don't get CO2. You don't get combustion is a complicated process. You get carbon monoxide, you get all this other stuff. I mean, but if you burn it at a high enough temperature, it's not so complicated. All the carbon just ionizes. Well, if you have an ion, right? Let's make this collector assembly really, really positive. Little negative, what would you call it, carbon ions or something, right? The negative carbon ions are going to be attracted to it. Every time it strikes, you'll have a tiny bit of current. Right, there we go. There's our transducer. Convert something chemical to something electrical. Okay, so you'll have your little electronic wire coming off of here into the PC, to the computer. Okay. So you can see it in the bottom. That's everything's coming off the column. If the column did its work, you have pure components shooting into this thing. Can this thing tell whether it's benzene or ethanol? It's just carbons, right? It's just a detector. Okay, but there has to be what there for it to get a signal? What type of ions? Has to be carbon, because FID is a carbon counter, right? If there's no carbon, you're not going to see anything. So what's something the FID could not detect? Like what? Oxygen gas, couldn't detect it. Hydrogen gas, couldn't detect it. Any of the noble gases? Yeah. Could it detect water? Water doesn't have carbon. This detector is fantastic for a problem that we came across with the environment. You take ibuprofen. How much of it does your body actually use? Yeah, it's a very small percent. So where does it all go? Down the toilet. And then what's even worse, I don't know if it's even worse, but people have old ibuprofen. They probably dump it. It's a bad habit. They dump it where? They should, but in the toilet. I don't know why, right? But anyway, that's probably it's probably not a big problem. The problem is just that's where all this stuff goes. Are all these drugs, do they evaporate easily? No, right? Do they break down easily? No. If they did, they wouldn't be, their shelf life would suck, right? So they're building up in the environment, and it's causing a problem. If you go up in Minnesota, you find the little froggies, right? There's supposed to be a problem going on there, but So what we wanted to do is we wanted to see if we could actually detect this stuff. And this detector turned out to be fantastic because what's your matrix? If I want to go out and get these samples in the environment, lake, stream, it's water. This detector is blind the background. It worked great. So the problem, but we found out, at first you hear this, oh, what the hell was that? And every time we injected, right? Right? And it like happened several minutes later after you inject. You have this big thing of water blowing through. What did it do to the flame? It put it out. So that was the only limitation. Somehow, but you got really nice signal. Okay. Using a C18 column, a sample of gasoline was injected on the gas chromatograph. An inlet temperature of 250, oven temperature 145. Okay, before I make up some little chromatogram there, is that an isocratic or a gradient run? Yeah, nothing's changing, so it must be isocratic. Yeah. Okay. So we've got signal on my GC chromatogram. My x-axis is time. Okay, so let's go. And maybe a gas is really complicated. There's going to be a gazillion peaks in there. Okay, so this is your first injection. You just guess, right? It's GC. You just shoot it in there. You just guess, and this is what you got. Do what's easiest first, and that's what you did. And maybe this is 3, 6, 9 minutes or something. Okay. So maybe before we make a suggestion how to fix it, maybe Adriana can tell us what's wrong, or what are some things that could be improved. Yeah, there's a, but in GC it's really not that big a deal. It's mobile phase, it's gas, so you're not really wasting a whole lot of money. You're just wasting the dude's time, right? So if you're paying somebody, then that's a problem. But if it's just you guys, a student, a summer researcher, I don't care, right? but I agree. That's, you could probably improve that somehow, and we'll talk about that. Is there anything else wrong? Yeah, I mean, look at all, there's a lot of stuff in here, right? If I could be a better artist, the guys, the early eluders, yeah, they look like they're resolved, fine. You can quantitate them. They're resolved. It goes down to the baseline between them. But the other stuff, the guy around the 3 minutes, okay, seems like a mess. So, Kathleen, what's a suggestion? What's that? Mess with the temperature? Okay, how would you mess with the temperature? And when? And how? Well, the why is that's the only thing she has to play with, right?
Yeah, pretty much. It's GC.
It's pretty much, that is the only thing she has to play with is the temperature. Any ideas? What could you do? I mean, I'm not saying you know what the result is going to be, that it's going to help it. I'm just saying, what could you do? Now you could, would this do anything? Good question. You could mess with it, but if it vaporized or vaporized, right? You're getting peaks, so that means it must have vaporized. So I wouldn't worry about it. Now, yeah, you could, increase it, fine. Oh, decrease it, fine. Decrease it, fine. When? Just do another isocratic run? Decrease it? Now, if you decrease it, what is your expectation? Things are going to, how is it going to change it if you decrease the temperature?
Spread spread out the peaks, I would think, at the 3 minutes.
Now you got to think of how you want to imagine this is the partitioning idea, right? You draw your column, you have your little liquid phase, right? Everything is shooting through the middle. What you want is, for right before the detector, you have pure components, right? Everything's nice and resolved, one band and then another band. If you increase the temperature, the partitioning, how is that affected? Would there be more here or more in the stationary phase if you increase the temperature? There'd be more, I guess, put it this way. If you increase the temperature, would there be more or less interaction with the stationary phase? It's less because it's a higher temperature, right? It has more energy. Look, kicked out of that stationary phase. So if you lower the temperature, you should be interacting more with the stationary phase, right? Okay. That's the general thinking. However, man, it's really complicated. So, and not everything is going to have the same influence, whether you increase or decrease the temperature. Some compounds, it'll actually reverse that effect. It's odd. So very often what seems to work is, I don't know, let's say everything is okay until 2 minutes. So why mess with that? So at 2 minutes, you could say keep it at 145. I don't care. I mean, it doesn't really matter. Just ramp. You could change the temperature and see what the effect is, whether it's higher or lower. And that might give you an idea of where to ramp the temperature. Ramping really, and this is only through experience, right? 145 to 210. And if you did the GC, you did ramp it, right? At 2 minutes, 145 to 210, I don't know, 10 degrees per minute or something. I don't know. You ramp it at 25 degrees per minute. Kick it up there faster, right? Maybe this way. Increase. At 2 minutes, increase. Or ramp. Ramp temp. And I'm not saying this is the right answer at all. I'm just saying this is what you try. And you could try that. What Ricky said. Just lower the temp. To a lot of your GC labs, what is the temperature of the oven? 40. Is that even possible? How does this even work? Because what's the boiling points of your compounds? Is it above 40? What is 40? What is 40 degrees Celsius? And I mean, just, is it this temperature we're at? What is room temperature in Celsius? Somewhere around there, right? Mid-20s probably. A warm room might be around 33, 34, right? So we're talking about kind of a stifling hot room, but it's not, super hot, 40. This stuff is still a liquid, right? It's boiling points. Man, if you read the little bottle like ethanol and things, they're around 80, 85 degrees Celsius. So you're way below the boiling point. How does this thing still work? Right? How does GC work if you're below the boiling point? This stuff should be a liquid. It shouldn't go anywhere. What goes on with all liquids? All liquids have a what pressure? A vapor pressure. What does that mean? What does that mean? All liquids have a vapor pressure. You can Google them. And as the temperature goes up, all the vapor pressures go up, right? Different compounds have different vapor pressures. You're saying it. Yeah. There's that equilibrium going on, right? So you always have a vapor. So by lowering that temp to 40, I was just taking full advantage of kind of what, full interaction with the stationary phase. And by keeping it isocratic, people have faster runs. You don't have to wait for the oven to equilibrate back down to the lower temperature. So isocratic is faster if you have multiple runs. Okay. So maybe at 2 minutes, ramp it, and then maybe at 4 or 5 minutes, you could really, maybe you could increase the flow rate. If you want this to come off faster, increase or decrease the temperature. Increase it, right? Kick it into that vapor phase, because there's nothing else there. You could crank it way up, and that would kick it out faster, right? So that's just the direction you want to head. You don't really know, you're just kind of guessing. And then there's a couple types of capillary columns. Okay, this is the most common one, stationary liquid phase. But it's different processes, different. You want different affinities. You want some different stationary phases if you're really getting particular. Okay. So there's a solid in there, or a stationary, kind of like that LC, those little, there's chemically coated spheres or something are in there. Okay. This lady, I could have swore she had them on. She should be wearing what? Why should she be wearing safety goggles, doing what she's doing? She's bending a piece of glass. That capillary column is glass, right? So here's one, and it's in a bag, so you can see that you can actually bend glass pretty easily there. But how can that glass bend? Emily, you can't bend glass, but you're bending it in there. So how's it possible to be bending that glass? Andy's right. It's just a curious thing with glass. If it's a ultra pure, you can spread it out and bend it like that. It has to be pure though. Okay. Now, if it's pure, it's also really reactive, especially to your grease and especially oxygen. So they coat it with this polyimide coating, right? And that's that orange stuff. Because what color is glass? Silica oxide. Glass should be clear, right? So why is this thing orange? That's the polyimide coating, right? It'll protect that ultra pure glass. So these capillary columns are just made out of glass, ultra pure glass. Otherwise, they're not going to bend on you. But it has to be coated, otherwise, right? It'll get stiff. React with oxygen, and it'll break at those points. Okay. Back to regular, typical glass that doesn't bend. Okay. Splitless injector. Be able to sketch. Okay. So to kind of give us some perspective here, we talk about a green nut, Ricky. Where would you guess this green nut would be? There's this green nut, and then you're supposed to put here he is, my syringe through there and inject the sample.
I'm going to hope that septum is the dead giveaway that I think it is.
Yeah.
There, yeah.
It's the guy that's surrounding the septum. That's going to be the green nut. That's the green nut.
No, dude, that's what I was saying.
Oh, you were? I thought you were talking about the
Stick
septum.
needle through the septum, and then it
Yeah.
does the thing around the needle.
All right, you got it then.
All that fun stuff.
Okay. It's supposed to say green nut. And I can't erase that for some reason.
I don't even know why I'm labeling it.
But that's just a green nut. It gives you, just to give you a perspective where it's at on the machine.
That's the end.
Okay. This is what if you've done GC lab, this is what you're setting at 50 to 1, 10 to 1, these split ratios. Okay? And then if you follow the logbook instructions and you're the 5th user, you're supposed to replace this septum. Right? And there's a septum in here.
Is it the 50s?
I think it is. I don't remember exactly what I wrote. Yeah, because it wears out. So it's just a hunk of rubber, right? And then there's so that the septum cap is our green nut, right? And then that little piece of rubber is a septum they have to change once in a while because it gets punctured by the needle a lot. And then there's this glass liner. And that's what this thing is. And this is in there in case Kathleen shoots, what is this?
Caramel.
Mama Chia's raspberry lemonade, right? You shoot that in the GC,
He didn't make that up, did he? Mama Chia.
you shoot that in the GC, what is not going to vaporize?
The sugar.
Sugar. So if without a glass line or something that I can just slide right out of there, you're going to be, I don't know how you clean it out, right? It'd be really a mess. Okay. Now these machines are extremely, extremely sensitive, and it's very easy to get overload, peak tailing, all this stuff. And a lot of these, like the MS especially, he can't handle high concentrations of stuff. Everything has to be really, really dilute. So you can go through all the work of diluting all your samples. I mean, it's just a waste. So that's why this splitless, handle it all in the inlet, right? Let's only take 10 parts and then 100 parts shoot out of the machine, right? Or split it 100 to 1, right? Only one part goes through the column. 99 parts go out of the machine. Okay, so there's all these different possible split ratios. Well, how does it all work? Well, you can see the split outlet, right? So if you have the split ratio set to 100 to 1, 99 parts of whatever you inject are going to shoot out the split outlet. The other part goes down the column, right? You can see the carrier inlet. That's our carrier gas, which is what gas?
Hydrogen.
Hydrogen. So that's coming from the what? Where's that coming from?
Giant gas.
The giant gas tank, right? That's our carrier inlet. So it looks like it's coming in up top here, right? And so your needle's in here. It's injecting everything. Hopefully everything vaporizes, right? Because the whole thing is set to, remember what temperature typically? That's the oven. The oven was 40. This inlet was set at 250. This is the one thing that needs to be above the what point? The boiling point. Of everything or just the solvent? You inject a lot of things in there, right? You're injecting solutions. Everything has a boiling point. Does this need to be above the boiling point of all of them? Or just the solvent? You're doing GC. Everything has to be a gas. Everything has to be a gas. This is the limitation for GC. It has to be dang hot. Why is that a limitation for GC and not for LC? Your stuff decomposes on you, right? If you want sugar to, you're not going to get it to happen because sugar is going to decompose on you. It's going to caramelize. Right? So there's a lot of stuff like that. This is an example of stuff like that. This is called Fowlis's rule. I don't know who Fowlis is, but he came up with the idea, and it actually really works well. We wanted to do something with, this is during the Iraq War and before NutraSweet was saccharin. And so I grew up with the saccharin stuff. And ooh, it's really, really bad for you. It's not near as bad for you as NutraSweet. NutraSweet decomposes to methanol, formaldehyde. This crap will make you go blind. Anyway, they have Iraq War, cases and cases of Diet Coke in the desert. So this stuff is under really high pressure, really hot. Does it decompose to this formaldehyde and methanol? That was our research project. GC is a lot easier to use than HPLC. Aspartame is our analyte. It has to, can we inject it? Will it vaporize? Well, you could try it or just do Fowlis's rule. If it dissolves in ethyl acetate, I don't know why this is, it just works. If it dissolves in ethyl acetate, it'll vaporize. Does it look like aspartame dissolves in ethyl acetate? No. Could I shoot it on the GC? No. You can try it, but it's not going to vaporize on you. you have to, it's a complicated process. To make it vaporize, you have to derivatize it. And that's a lot of work. You got to know organic chemistry to do this. Okay? Derivatize. You have to chemically modify that compound so that it will vaporize and not decompose on you. Okay. Okay. So there's 3 ways for this stuff to get out of the inlet. Oh, let's mention split less first. If you're going to operate the inlet in split less mode, what does that mean? Everything you inject goes to the column. Exactly. What are the 3 ways that the sample can leave the inlet? There it is. Purge outlet. Where did you see that? Oh, there it is. Here's one. Septum purge outlet. Split outlet. Yeah, you're right. The column. All right. What is the, so we talked about the split outlet. All right. Column makes sense. What is the purpose of the septum purge outlet? Septum purge. I'll give you a hint. I think I talked about Sam's, the tire aisle. All right. I'm one of the oddballs who loves the smell of gasoline, and but I love even more the smell of tires. You can have one new tire that it fills up the whole room with the odor, right? Rubber constantly just emits gases, constantly. You can't stop it. That's just how rubber is. You think by the year 2013, we'd have developed a compound that's spongy, that you can put needles through? That's not rubber. Have we? No. What? Since we haven't. Since we have to use rubber. And it's constantly emitting gases. Big problem for the GC because that's what we detect. All you're going to detect is the freaking gases from that little tiny rubber septum. And they heat the crud out of these things to try to get all the gases out. They still can't get it out. Your background is tremendous if you don't constantly blow carrier gas up here, right below the septum, and just kick it immediately out. You still get a lot. Right? You don't inject anything. You have a signal. That's all septum. It's all septum. And it's some bleed from the column, but it's mostly septum. Okay. So that's the purpose of the septum purge. But you will lose some sample through there, I guess. Okay. Last thing to mention is the flow calculator program. Well, I can mention that next time. I'll mention that next time. So that won't be on the quiz anyway. All righty. So have a good day. We went over by 3 minutes. Sorry.